Hey Calc BC, welcome to lesson 3.6, Accumulation of Functions and Definite Integrals. This is our third lesson from College Board's Unit 8, Applications of Integration. This lesson in College Board is specifically called Using Accumulation Functions and Definite Integrals in Applied Contexts. If you dig a little deeper into College Board's breakdown of this lesson, we have the essential knowledge, which is a function defined as an integral represents an accumulation of a rate of change. The definite integral of the rate of change of a quantity over an interval gives the net change of that quantity over that interval. And the definite integral can be used to express information about accumulation and net change in many applied contexts. And that's really what this lesson is going to be about. It's going to be applying integration through many different contexts, and we're going to look at graphs, we're going to look at table, we're going to look at a function defined by an expression, and we're going to see different accumulations within each of these. You're not going to necessarily learn a brand new formula in this lesson, but it will be kind of like piecing a lot of things together to make sure that we are comfortable with the idea of accumulation function. So I'll pause now and we'll get to the notes. All right, so here are our notes for 3.6, accumulation of functions and definite integrals. The definite integral as an accumulation function and the net change theorem are two important concepts in AP calculus and are often tested in problems in context. This section provides a brief summary of results and several problems involving these concepts, some in calculator active questions. Example 1. Let f be a function defined on the closed interval from -4 to 4 with f of 0 equals -3. So we're given an initial condition of f. The graph of f prime, the derivative of f, consists of one line segment and a semicircle as shown in the graph below. And as always, it's very helpful if they tell us that this is specifically a line segment and a semicircle, because that's going to help us with area, right? We can't just kind of assume that this is actually circular with a radius, but since the question tells us it is, now we can assume that. But let's look at letter A. On what intervals, if any, is f decreasing? Justify your answer. So I drew a chart over here on the right before I started filming just to show you what I like to think of as like a cheat sheet for a function, first derivative and second derivative. This goes back to Calc 8b, of course. But if f is decreasing, we know the first derivative will be negative, right? So I'm actually going to write that out as part of my justification. I'm going to say f is decreasing when f prime of x is less than 0. And therefore, the intervals where f is decreasing is only from x values of 2 to 4. Okay, let's look at letter B. Find the x-coordinate of each point of inflection on the graph of f in the open interval -4 to 4. Justify your answer. Points of inflection, if we look back up at our chart, points of inflection are when we change concavity, right? From concave up to concave down, or concave down to concave up. And we know that this happens when the second derivative either equals 0 or doesn't exist, and the sign switches from positive to negative or negative to positive. You can see that's kind of matching up on our chart here. But we don't have either of those. We have the first derivative graph. And so on the first derivative, it's about when the f prime switches from increasing to decreasing or decreasing to increasing. So if we look at our chart here, we are decreasing and then we switch to increasing at an x value of -2. And then we switch from increasing to decreasing at an x value of 0. And those are the only kind of relative maxes or mins that show up on the f prime graph, which are causing these inflection points. So I'm going to write all of that as my justification with my answers. So I'm going to say inflection points happen when f double prime equals 0, or if it doesn't exist, and it changes sign. So f prime changes from increasing to decreasing, or decreasing to increasing. And the x values that work on our chart are -2 and 0. And that's because at -2, we switch from decreasing to increasing. And at 0, we switch from increasing to decreasing. Okay, that brings us to letter C. Find an equation for the line tangent to the graph of f at the point 0, -3. Okay, so let's see. We are trying to find the tangent line. So in calculus, I think it's always helpful to use the point slope form of a line, because all we need to do is plug in a point and the slope. So in order to plug in here, we need our x1 and our y1 and our slope. And so if we look up here, we were told that f of 0 is -3, and part C told us it again, that there's a point 0, -3. So that's our x1 and our y1. The slope is, going to come straight from the y value of our first derivative graph. So if we take a look, we're looking at an x value of 0, and our y is at 2, right? So we know that the slope on the original graph is going to be 2. So we can plug in here, we get y plus 3 equals 2 times x minus 0. And that's technically a valid answer. You can leave it like that, but I'm going to solve for y just to kind of give some conclusion here to get y equals 2x minus 3. And if we sketched that line and we were able to see the parent or the original function that caused this derivative, we would see that this is a tangent line for x equals 0. Letter D, find f of -4 and f of 3. So we're going to use the fundamental theorem of calculus to do this, but rearranged. And this will hopefully look familiar to you. To find f of -4, right now the only value that we know on the original graph is f of 0. So we're going to start with f of 0. And because we are going to go to the left to get to -4, I'm going to subtract from -4 to 0 of f prime of x dx. So hopefully that makes sense. There's some area from -4 to 0 on this graph. If I figure out what that area is, and I subtract it from f of 0 because we're going to the left, then we should be able to get to f of -4. We're going to do the same thing for f of 3, but 3 is to the right of 0, so we can add from 0 to 3 f prime of x dx. All right, so that's the difference there. So let's try to figure this out. We were told that f of 0 was -3. And for the first one, we're subtracting the area that's below this curve, which we were given was a semicircle. So the area is this rectangle right here, which has an area of 2 times 4. So we're starting with 8. And then we're going to subtract the semicircle to get the kind of the region that's under it. So if I subtract this, it has a radius of 2, so pi r squared is pi times 2 squared, so it's 4 pi, but it's only half the circle. So yeah, it's only half the circle, so instead of 4 pi, it's 2 pi. And so then when we calculate this, we got to distribute that negative, and we get -11 plus 2 pi. And we can do the same thing for this one, except now we need the area from 0 to 3. So from 0 to 3, we have this triangle up here, which is going to be 1/2 times 2 times 2. And then we have this triangle down here, which is below the x-axis, so it's negative. So we're going to subtract that triangle, which is 1/2 times 1 times 1. And so we'll get -3 plus 2 minus 1/2, which is going to end up as -3 plus 1/2, which will be -3/2. And there's our two answers. All right, so that is the end of example 1. Let's move to example 2. Let f be a function defined on the closed interval from -6 to 6 with f of 0 equals 3. The graph of f prime, the derivative of f, consists of 1 semicircle and 4 line segments as shown in the graph. So this is pretty similar to example 1. We've got line segments and a semicircle, and this is the graph of f prime, and we were given an initial condition for f. So very similar. But let's see how we can approach these questions. For -6 to 6, find all values x at which f has a relative minimum. Okay, so what we need to remember is that if there's a relative minimum for f, that's when the first derivative is going to change from negative to positive, right? Because that's telling you that in the initial graph, we're changing from decreasing to increasing, just causing that relative minimum. And you can look at that chart from the first page again if you want to see what I mean. But f prime changes from negative to positive at x equals -4 and x equals 2. Therefore, f has relative minima at those values, x equals -4 and x equals 2. And you can see that right here, it changes from negative to positive, and right here it changes from negative to positive. Letter B, from -6 to 6, find all x values at which the graph of f has a point of inflection. Okay, so just like in the last problem, we know that points of inflection happen when the second derivative equals 0 or does not exist, and it has to change sign. So that means that we're looking for places on the first derivative graph that changes from increasing to decreasing or decreasing to increasing. And since we have a continuous first derivative graph, we're really looking for relative maxes and relative mins. So that's going to be at x equals -3, x equals 0, and x equals 3. Okay. Letter C, find all intervals on which the graph of f is concave down and increasing. So the graph of f, we want to know when this is concave down and increasing. So I want to know what on the f prime graph is going to cause this. If the f graph is concave down, the f prime graph is decreasing. And if f is increasing, the f prime graph is going to be positive. And this, again, you can get from that chart that we drew in example 1. Go back and look at that part of the video if you didn't write that down. So we are looking for on our graph when we're decreasing, but also positive. So above the x-axis, but decreasing. And that happens from -3 to -2 and from 3 to 5. So that's what I'm going to write here. Okay, that brings us to letter D. Now, I already wrote out some of this because I knew it would take me a long time to write, and I didn't want to waste your time in this video. But feel free to pause if you need time to write this down. But what this question asks for is to find the absolute maximum value of f of x over the closed interval from -6 to 6. So we're going to use the candidates test for this, but it's going to take us a little bit of effort, as you can see, because we don't have a function. We don't have an initial f function, or an equation at least. So we're going to definitely check the endpoints of the interval. And since we're looking for the absolute max, I'm going to specifically pull out anywhere where there could be a relative maximum. If there's a relative minimum, that's still a critical number, but we know for sure that's not going to be the absolute max because it's a minimum. It's lower than even x values that are close by. So at -2 and at 5 is when our graph changes from positive to negative. So that is going to cause a relative maximum in the F graph. So what I've done here is use that fundamental theorem of calculus to write out expressions that will represent each of these values. So again, we were only given f of 0. So to find f of -6, we're going to start with f of 0 and then subtract the integral from -6 to 0. We'll do the same thing for -2, and then 5 is to the right of 0, so now we're adding from 0 to 5, and for 6, we're adding from 0 to 6. So f of 0 was 3, so all of these start with 3. For the first one, we need to figure out a whole bunch of stuff, right? Because we are going from -6 to 0, and we're going to subtract that. So from -6 to 0, first of all, we have this chunk over here, which is a triangle, 1/2 times 2 times 2. That's going to be -2. We've got this triangle that's above the x-axis, 1/2 times 1 times 2, which is going to be +1. And then we're going from -2 to 0 to finish this off. So we've got a quarter of a circle with a radius of 2. And we're going to subtract that area. So we've got pi r squared, so 4 pi, but only a quarter of that, so pi. So it's going to be -pi. And if we combine all of this, we're going to end up with 4 plus pi. All right, for the second one, we're only going from 0 backwards to -2, or really from -2 to 0. So we start with 3 and we subtract. And this was just the part from -2 to 0. So it's a -pi. So this is 3 plus pi. For f of 5, now we're going from 0 all the way to 5. And this time we're going to the right, so we're going to add it. And we have, again, a quarter of a circle, so it's going to be -pi. And then to 5, we can count that all as one triangle above the x-axis, 1/2 times 3 times 2. That's going to equal 6 minus pi. And then for the last one, we're doing that whole thing again. And then we have one extra little piece to get to the 6. It's going to be minus 1/2 times 1 times 1. And that equals 11/2 minus pi. Okay, so what we're going to do then is kind of look at all of these and figure out which one is the largest. And if you calculate these by eyeballing them or by typing them in and looking at the decimal on a calculator, what you're going to find is that 4 plus pi is the biggest. So we have an absolute max of f of -6 equals 4 plus pi. All right, and that is the end of example 2. All right, let's move to example 3. The rate at which water is processed and stored in a tank at a water utility company is modeled by the function R, given here, and that's in the units of thousands of gallons per hour, and T is measured in hours. And 0 is less than or equal to T is less than or equal to 8. Water flows from the storage tank to the community at a rate modeled by D of T. There are 200,000 gallons of water in the storage tank at time t equals 0. Part A, how many thousands of gallons of water are processed and stored in the tank during the 8-hour time interval from 0 to 8? Okay, so for this specific question, we just want to know how much water is processed and stored. And that is this R of t function. We're not really caring right now about how this water flows from the tank to the community. We just want to know how much is actually processed. So to figure that out, we have the rate. So we are looking for like the amount, right? Which is kind of one step up from the rate. So we're looking for the integral from 0 to 8 of R of t dt. All right, and this is one of the calculator active questions that we're going to be looking at today. So to help us out here, I already went ahead into my calculator and I pre-typed in R of t as y1 and d of t as y2 so that we can use these multiple times throughout this example. So go ahead and type those in now in your own graphing calculator so you can practice doing this. And to solve this first integral, now that we already have R of t in y1, all we need to do is set up the integral. So I'm going to go to math 9. I'm going to go from 0 to 8. And I'm going to go to vars, y vars, number 1, and number 1 again to get y1. And I'm not going to plug in any number for x. I'm just going to leave it as x. So I have to do y1 of x dx. And we get 16.576. So that is our answer. And we need to make sure we put units, and that is measured in thousands of gallons. Right, R of t was in thousands of gallons per hour. We went one level up, so it's just the singular gallons units, not per hour. All right, part B is the amount of water in the storage tank increasing or decreasing at time t equals 4 hours. All right, so think about this is like a rate in, rate out problem, right? So we have amount of water that's going into the tank and the amount of water that's leaving the tank. So if this is kind of like what the tank looks like, we've got the R of t that's pushing water into the tank at a specific rate. And we've got the d of t that's pushing water out of the tank at a certain rate. And the water level inside the tank might be rising or lowering based off of which of these rates is larger, right? So specifically for this question, what we might do is figure out R of 4 minus D of 4, right? Because this is the rate in, this is the rate out. If we subtract these values and we get something positive, we know that the rate in was larger, so we're going to be increasing the amount of water in the tank. If we subtract these values and we get something that's negative, it means that the D function was larger, which is our rate out, which means the amount of water in the tank is decreasing. So let's try this on my graphing calculator. I can just type in, now that I have y1 and y2, I can go to vars, y vars, grab y1 of 4 minus vars, y vars, whoops, I wanted y2, vars, y vars, y2 of 4. And I get 0.282. Remember, in AP Calculus, you always want to round to at least 3 decimal places. And that is greater than 0 last time I checked, which means, therefore, the amount of water in the tank is increasing at t equals 4 hours. There we go. Moving on, part C. At what time from 0 to 8 is the amount of water in the storage tank a maximum? Justify your answer. Okay, so we need to know now really what the initial function is here, right? What would our f be if we're given f prime, right? So what I would like to think about this is the amount of water in the tank had an initial condition of 200 that was given to us in the problem stem. And then we could add from 0 to some time t of r of x minus d of x dx, right? So if you think this is the rate in, this is the rate out. If we subtract those two, do the integral of the result, we're getting kind of the amount of water that's either added or subtracted from the initial 200 at a given time t. So if we take the derivative of that, we just get, you know, the 200 goes away, it's a constant. The derivative of this is just going to be r of t minus d of t, right? That's that second fundamental theorem of calculus, where we're going from 0 to a variable, so we can just plug t in for x. And that's our derivative. It's a derivative of an integral, right? That's how we do that. So what we are looking for here is the critical numbers, right? Critical points that we can use to run a candidates test to find the maximum. So we want to know, when does r of t minus d of t equal 0? And since this is calculator active, I'm going to go back to my calculator and I'm going to look at the graph of those functions. Remember, I have y1 and y2 in here. That's r of t and d of t. I want to know when we subtract them and we get 0. We're going from 0 to 8. And I can see if we subtract them and get 0, it's talking about their intersection points, right? So I can see that there's two places where these intersect between 0 and 8. And I'm going to find those values right now. The first one is at an x value, or in our case, a t value of 1.329575. And since this isn't my final answer, I'm going to try to be as precise as I can by keeping all those decimal places. I don't want to round until I get to the very end. And I'm going to find the other intersection point, which right here, they just kind of go next to each other, but don't intersect until they get all the way over here. And this one has an x value of 7.589946, etc. Okay, so then I'm going to set up my t and a of t to see which one of these is the actual maximum. We got to include our endpoints and then these t's. So we got 1.329, etc., 7.589, etc. Those are the t values we're trying. So for a of t, I'm going to go in and plug each one of these in, replacing t with this number. And to make things simpler here, I already did this, but you could do it on your home screen, or you could do it in y equals in the table or in the graph to make this easier for you if you would like. But here are the results. So the first one is 200, because we didn't go anywhere yet. We went from 0 to 0, so it's just our starting value. Second one is 198.676. Third one is 201.646. And the last one is 201.473. So the water is a maximum in the storage tank at t equals 7.589. Okay, and we did a candidates test, which is a valid reasoning or justification for our answer. So we're good. All right. Example 4, the rate at which people enter the Naples Zoo on a given day is modeled by the function e, defined by e of t given here. The rate at which people leave the zoo on the same day is modeled by the function L, defined by L of t. Both e of t and L of t are measured in people per hour, and time t is measured in hours after 8 a.m. These functions are valid from 0 to 12, the hours during which the zoo is open. At time t equals 0, there are no people in the zoo. All right, let's do this. Part A, how many people have entered the zoo by noon, or t equals 4? All right, this is very similar to the beginning of example 3. So we're going to set this up as an integral from 0 to 4 of our E of t, which is the rate people are entering. Okay, so what I could do is type this into my calculator. I'm going to pause right now and get that set up so that I can show it to you. All right, so you can see that I've typed in the E of t and the L of t as y1 and y2. So that's going to help us throughout this whole example. So I'm going to leave those in there. But for this specific one, we want y1 because we are going to be integrating from 0 to 4 E of t, which was our rate in. So I'm going to go to math 9. I'm going from 0 to 4. And I'm going to go to vars, y bars, function y1 of x dx. And this is 203.068. And approximately 203 people have entered the zoo by 12 o'clock p.m. That's what that means. Okay. Letter B, 20% of the people who leave the zoo receive a special discount ticket for a return trip to the zoo. How many people have received a discount ticket by 5 p.m.? T equals 9. Okay, so let's figure this out. We need to know how many people left the zoo. We have our rate out function, which is what we're going to use for that. So we are specifically interested from 0 to 9 of L of t dt. And that's my y2. So I'm going to do math 9 from 0 to 9, bars, y bars, y2 of x dx. And I get 395.902. 20% of those people are going to get these discount tickets. So I'm going to do 0.20 times 395.902. And I get 79.180. And that is approximately 79 people. It's bothering me that I didn't box the answer in the previous one. Okay. Letter C. Let n of t be the integral from 0 to t of e of x minus L of x dx for 0 to 12. Find the value of n of 10 and explain the meaning. Then find the value of n prime of 10 and explain the meaning. So n of 10, let's start with that one. So we're going from 0 to 10 of e of x minus L of x dx. And we should be able to do that right on our home screen with our y1 and our y2. So let's grab another integral. I'm going to go from 0 to 10. And I want y1 of x minus y2 of x dx. Okay? So we end up with it's working. 273.635. So what that means is approximately 274 people were in the zoo at that time. Which was 6 o'clock p.m. Okay, so that's the first answer. Question also says to find n prime of t. n prime of 10, rather. So finding the derivative here of this. Okay, so I'm going to pause real quick and we'll get into that. All right, so for this part, we already have the integral here. So to take the derivative, remember, it's that second fundamental theorem where we're going to be, if we think of this as from 0 to t, like it is in the question, to take the derivative, we're just replacing all the x's with the t's. So to find n prime of 10, it's just going to be e of 10 minus L of 10. So that's what we're going to do now on our calculator. So forget the integral. We're just doing y1 of 10 minus y2 of 10. We get negative 6.228. 228. And what that is telling us that the number of people in the zoo was decreasing at that rate. So the number of people in the zoo is decreasing at a rate of 6.228 people per hour. Specifically at that time. We should probably add on at t equals 10. Okay. Letter D, at what time t from 0 to 12 does the model predict the number of people in the zoo is at a maximum? Justify your answer. All right, so the total people in the zoo is going to be, that's that function that we were just looking at in part C, right? That's the number of people in the zoo at a specific time. Because we started at 0, and then this is kind of doing our rate in minus rate out to figure out how many people are in the zoo at a specific time. So we're going to start with that function. And we also know that the derivative is e of t minus L of t. So we're trying to figure out a maximum, so we need to know our critical numbers. So we want to know, when does e of t minus L of t equal 0? And that happens if we use our calculator and we take a look at the graph and figure out, when does e of t equal L of t? What you're going to find is that it happens one time, although I think my viewing window is going to be a little bit messed up here. Yeah, we're not going to be able to see it. So I'm going to change my window to Zoom Fit to see if that helps. Okay, so the x-axis is still from negative 10 to 10. So we want to answer from 0 to 12. And there, you can see it right there. So I'm going to figure out, what is that intersection point? Okay, and it's going to be about 8.134. Now, if I didn't already know that that was the only point, because I have an answer key that I already created, I would want to change my window to go from 0 to 12, just so that I could make sure that there wasn't another intersection point beyond x equals 10 that I didn't already see. But I already know that this is the only one, so I'm going to set up my chart for my candidates test. We're going from 0 to 12, and there's one critical number. And if I plug each one of these into this, I already have the answers, but you could do that on your calculator. You would get 0, 281.117, or 260.905. So our maximum occurs at t equals 8.134 with approximately 281 people. Okay, so there you go. Very nice. All right, one more example. Let's look at example 5. This one uses a table. The cows on a small dairy farm in upstate New York are milked in the morning during a 2-hour period. Milk from the cows is pumped into a storage tank, and the volume of milk in the tank at time t is modeled by a strictly increasing, that's going to be important, twice differentiable function m. So that means at every point of m, there is a first and a second derivative that's possible. Where m of t is measured in gallons and t is measured in minutes. At time t equals 0, there are 300 gallons of milk in the storage tank. Values of m of t at selected times t are given in the table. Estimate m prime of 70. So we don't have t equals 70 in our table, but we have 50 and 90, and 70 is perfectly situated halfway between 50 and 90. So to estimate the slope or the derivative at 70, we're going to have to approximate it using those values close by. So we're going to do m of 90 minus m of 50 over 90 minus 50, our good old-fashioned slope formula, right? y2 minus y1 over x2 minus x1. So we get 3360 minus 1640 over 40, and if you calculate that, you're going to get 43. We need to indicate units of measure and explain the meaning of the answer. So what we're going to say is the volume of milk in the storage tank is increasing at a rate of approximately 43 gallons per minute at time t equals 70 minutes. All right, so we said what our units were. We said what this number really means. The volume of milk in the storage tank is increasing at this rate. And we said what time or what x value, or in this case, t value, we are referring to. Okay, so all of that is important when you're indicating units of measure and explaining or justifying the meaning of your answer in context. All right, letter B. Use the data in the table to evaluate the integral from 0 to 120 of n prime of t dt. All right, so here we go. So we have 0 to 120 n prime of t dt. And we can think about that the integral of n prime is going to be m. We're going to evaluate that from 0 to 120. So that really just means m of 120 minus m of 0, which is 4250 minus 300, or 3950. All right, so that's the integral. And again, we need to use correct units and interpret the meaning. So we're going to say the volume of milk in the storage tank has increased by 3950 gallons over the interval from t equals 0 to t equals 120 minutes. All right, so you can see that that's really what our math did, right? It found the difference between 120 and 0. So it's finding that we increased by 30,950 gallons over the interval, okay? We didn't take an initial condition into account in that question. Part C, use a right Riemann sum with 4 sub-intervals indicated by the data in the table to approximate 1 over 120 times the integral from 0 to 120 of m of t dt. So let's start with that. The 1 over 120 can just kind of hang out there. We don't need to do anything with that yet. And we're trying to do 4 sub-intervals with a right Riemann sum. So if we take a look up here, our first interval is going to be from 0 to 20, and we're going to multiply that by 780. From 20 to 50, that's a width of 30 times 1640, then a width of 40 times 3360, and then a width of 30 times 4250. So we're going to write all of that out. And if you multiply that together, you get 326,700, which then multiplies to get you 2722.5. So then we need to explain the meaning of this expression in context, and that would be that this represents the average, right? Because that's the average value of a function formula. So it represents the average volume of milk in gallons in the storage tank from 0 to 120 minutes. And last thing, does this approximation overestimate or underestimate the exact value of the integral? So if we go back up and look, in the question it told us that this is strictly increasing and differentiable, which means it's continuous and increasing. So if you think about a right Riemann sum, each of those bars is going to be kind of including a region that's not in the actual graph, right? Think about a strictly increasing function. It might not be a straight line, but every bar for a right Riemann sum is going to have a chunk above the graph. So that means that this is an overestimate because there's parts of our Riemann sum, parts of our bars that's outside of the region. So we can write that it's an overestimate. Because m of t is strictly increasing. Okay, so that's it. That's the end of the notes. Thank you so much for watching, and let me know if you have any questions. Thank you.